you have different types.
So in today's lecture, we are going to talk about classification of partial differential equations. Like we have discussed in the previous classes, we usually have our governing equation as a set of partial differential equations, or as a single partial differential equation, which can also be written in the integral form. So to analyze the physical behaviors and to see what class of PDEs represent what kind of physical flows and other problems, we need to it's a good idea to classify the partial differential equation. So in general, especially for CFD, we can classify based on the physical behavior. We can classify our problems as equilibrium problems, and marching problems. So equilibrium problems are those problems for which a state of equilibrium is attained, and for marching problems are essentially transient, unsteady problems. Okay. They're usually, not usually, always transient, unsteady. But there is I think there is a special case of time marching problem for which steady state is possible. Steady state in the sense that we will see that later. So for equilibrium problems, you always have a steady state. Problems. So many steady state problems are governed by elliptic equations. So let's start classifying the equations. Okay, so elliptic equations are described using Laplace equation. So it's essentially so for a 2D case, this will be the prototype of the equation. So this is nothing but this is del square phi, right? Del square of phi is equal to 0. So a good example is steady state heat conduction. An example would be steady state heat conduction, and for steady state heat conduction, of course phi here is equal to T, And you are actually familiar with for one dimension, you know that k d square dt d square t over dx square equal to 0 is followed by the one dimensional heat conduction problems. So for a 2D case, you will have one more term, and which is similar to our prototype. So this for all the steady state problems, we usually need an initial value or a boundary value. So these are all boundary value problems. So for example, in this case, if you have a road with two ends kept at different temperatures T and TB, so these are our boundary conditions here. For if our axis is if our coordinate, one dimensional coordinate is in this direction, let's say for x is equal to 0, you have t is equal to ta, and for x equal to L, you have t is equal to TB. So that will be our boundary condition in this case. I think I used the term initial value for this example. That's not actually true. Initial, you only need boundary values for steady state problems. You need initial values for unsteady problems, time marching problems. Now for unsteady problems, for unsteady problems are usually for CFD, they're governed by either a parabolic equation or a hyperbolic equation. So let's first talk about parabolic equations. So parabolic equations are equations of the class dou phi dou t is equal to a constant multiplied by dou square phi dou x square. Right, this is the prototypical equation. So yeah, so an example of this would be transient heat conduction. So what is the difference between steady state heat transfer and transient heat transfer? Transient heat transfer, you also have the time variable. So depending on the time, the temperature changes. Temperature or heat transfer changes. So the process is essentially time dependent. So just like the previous case, we can put phi is equal to t and get a transient heat conduction problem. So for these problems, if we take the same example of a bar with two ends if the two ends have a prescribed temperature, we usually have a steady state problem. If this is 100 and this is 50, the heat transfer occurs in a certain direction, a given direction, with no time dependent changes. So for time dependent problem, you have to the case could be T temperature at A can be a function of time. If that is a function of time, so TA changes, the specified temperature here changes, that depends on the temperature, and that makes the problem a transient heat diffusion problem. This part may also depend on the time, and there can be several cases. So that will be an example of a parabolic equation. The next class of equations are called hyperbolic equations. So what are hyperbolic equations? So a prototype of the equation will look something like this. Now what is the difference here? Looks very similar to that of the parabolic equation, but you have second derivative of phi here. And you can actually see that this second derivative with respect to time, that's something we usually have in if you think about if you remember your lessons in mechanics, that this is something, the acceleration is a quantity that comes to our mind when we take the second derivative of a quantity. So if that is if phi is displacement, you have second derivative of displacement will be acceleration, and that's a term there. And so this class of problems, hyperbolic equations, usually this is very commonly used for vibration problems. And another factor to remember here is diffusion is usually high for parabolic equations, and diffusion of energy is actually small. No, diffusion is not the right term. Dissipation of energy is low for this class of problems. So if you remember the equations, governing equations we use in vibrations, you will know that that falls into this category. This is quite similar. And its solution of these equations usually will have in vibration we usually have the trigonometric functions in the solution, so it's always so the solution y is usually cosine of something multiplied by sine of something, so that kind of solution is usually present for vibration problems. So this is just a very brief introduction to what type of equations we deal with, and let's I think this table will be very useful for you. So this essentially you can see the very important features of three types of equations. And first you have the elliptic equations, which is usually used for equilibrium problem types. The prototype equation is given, div grad phi. So what is div grad phi? There is del dot del phi. So it requires boundary conditions. Solution domain is closed, and solution is always smooth. And you have the parabolic equations next. The prototype equation, which we have discussed already, it requires it, and hyperbolic equation requires initial and boundary conditions. The solution domain is open, and for hyperbolic equations you can have discontinuous. There may be a possibility of discontinuous solution there. And there is a technique that you can use to remember, not to remember, to find out whether a PDE belongs to which class of problems. Let's say we have a general second order PDE with x and y are as independent variables and phi as dependent variable. So what could be the format of a very general case? It could be second derivative of phi with respect to x. Now I told you that x and y are the independent variable, so there will be a case with mixed derivatives, and dou square phi dou y square, and these are the higher order terms. And then you have lower order terms first order terms, which will be dou phi by dou x and dou phi by dou y. A term with no derivative and one constant. So we can assume that A, B, C, D, E, F, G are constants. That doesn't need to be the case. It can be a function of x. Let's for the time being assume that these are constants. Now and now so the classification of PDE, it's governed by the highest order derivatives. So which are the high order derivatives? These three are the high order derivative terms. Depending on existence of roots of characteristic equation. Okay, I'll just write down a characteristic equation here. So depending on the number of roots of this characteristic equation, you have different class of problems. So how do we find out the roots of this equation? So the behavior of the roots will essentially be described by b square minus 4ac. So we know that if b square minus 4ac is if it is greater than 0, you have if this is positive, you have two real characteristics. If it is equal to 0, one real characteristic, and if it is less than 0, you have no characteristics. So in the first case, this will be hyperbolic equations, and these will be parabolic equations, and this will be elliptic equations. So if you have a given equation, you can actually find out whether the given equation is hyperbolic, parabolic or elliptic using this idea. Just find out for b square minus 4ac, check whether it has check whether it is greater than 0 or equal to 0 or less than 0. So in some cases A or B, these coefficients can be a function of x or y. So in those cases, depending on the range of values for x and y, you will have different types of problems. So you will have to say for y, for a certain values of y, equation could be hyperbolic. For certain values of y, equation could be parabolic. For certain y values of y, equation could be elliptic. So that can be the case if these coefficients are a function of x and y, or just x or y. So this is something, this is a useful formula that you can remember to figure out what class of problems a particular PDE falls into.